Hello everyone and welcome to the video on section 10.5 dealing with the binomial theorem. The binomial theorem really gives us another way to expand a binomial. So when we take like x plus 4 to the 7th power, instead of multiplying it out term by and getting it that way, the binomial theorem gives us a faster way to do that. So our skill objectives for this particular video are 1, evaluate a binomial coefficient with the binomial theorem. Number 2, evaluate a binomial coefficient with Pascal's triangle. Number 3, expand a binomial using a positive integer power. And number 4, find a particular term of a binomial expansion. Conceptual objective is really to recognize the patterns in that binomial in any binomial expansion. One thing you need to remember is that a binomial is a polynomial that has two terms. So a plus b would really be what we're looking at. And when we talk about a binomial expansion, what we're doing, we're talking about taking a binomial and raising it to an integer power. So our binomial expansions here, we have a plus b to the first would be a plus b. A plus b to the squared is going to be a squared plus 2ab plus b squared. If I multiply a plus b to the third out, I'll get a cubed plus 3a squared b plus 3ab squared plus a to the third. If I take it to the fourth, I will get this. And if I take it to the fifth power, I will get that. Now, one thing I would like you to do is be sure to have access to these 5 expansions because we're going to need to look at these again later on. But some patterns that you should recognize on here. Number 1, in this case, look at the power that you're dealing with. And then look at the number of terms. You'll notice that when we took a binomial to the first power, we have 2 terms. When we took it to the second power, we have 3. When I take it to the 5, you notice I will have 6 terms, and that will always be the case. So one thing you have to remember is that when you do a binomial expansion, you're going to have one more term than the power that you're dealing with. Another thing I want you to notice that as we have it written out here, the powers on A start at whatever this power is, whatever n is, if you will, and it works its way down until really you don't see an A, but you can think of that as a to the 0. And the powers on B start basically, think of that, you don't see a B, but think of it as b to the 0, and work its way up all the way to whatever n is. Another thing you should notice too, just pick one of the terms. It doesn't matter which one. And like if I take this particular term right here, you take the powers that you have on A and B, add them up, you'll always get the power that you're looking at here. In this case 5, 2 plus 3 was 5. Here it's 1 on A, 2 on B, so that's 3. Here 8 is to the third, B is to the first, 3 plus 1 is 4. So you have that one. Also, the other thing I want you to do is look at what are called the binomial coefficients. And the binomial coefficients are really the coefficients that you see, the numbers that you would see in front of the A and B. So, in the first case right up here, we have it would be 1. Yep, let me put that here. Be 1 and 1. Then the second one is 1, 2, 1. In the third one, the binomial coefficients are 1, 3, 3, 1. And then fourth, it's 1, 4, 6, 4, 1. And in the fifth one, it's going to be 1, 5, 10, 10, 5, 1. And you'll notice the pattern that happens there, that they work their way up, 1, 5, 10, and then work their way down, 10, 5, 1. And it's symmetry. Here, 1, 4, 6. In this case, when you have an odd number of terms, the middle number is not going to be repeated. It's 1, 4, 6, 4, 1. So that's another pattern that you're going to see with these binomial expansions. So really, in terms of going through and doing a binomial expansion, writing it out, we have a couple things we have to be able to find. Number 1, we have to know what A and B are. And those will be obvious when we look at the problem. Whatever's in that first spot is A, whatever in that second spot is B. We have to know what n is. N is going to be the power we're raising it to. But the other thing we have to be able to do is we have to find these binomial coefficients. Okay? And that's what our next slide is going to help us find. So what we have here is a definition for binomial coefficients. This is how we can find this. Okay, it's for non-negative integers n and k, where n has to be greater than or equal to k. This symbol right here has the parentheses and n and k over it. Kind of looks like one of those vector symbols, but it's not. Is called the binomial coefficient and is defined by that this symbol is read as n choose k, as n choose k equals n factorial over n minus k factorial times k factorial. For example, if I want to find 9 choose 6, I know it's going to be 9 factorial over 9 minus 6 factorial times 6 factorial, which that's 9 factorial over 3 factorial times 6 factorial. And now we have to just simplify this. So remembering that I know that 6 factorial is going to be a factor of 9 factorial, I expand the 9 factorial to be 9 times 8 times 7 times 6 factorial over 3 factorial times 6 factorial. The 6 factorials drop off, and so I have 9 times 8 times 7 over 3 times 2 times 1. And multiplying that out, I will get that as being 84. So what I'd like you to do right now is pause the video, and I would like you to find 7 choose 5. Welcome back. You should have gotten, when you did 7 choose 5, you should have come up with 21. If you need to, take a look at the work that I did on that one. But now we're going to talk about, on the next slide, we'll talk about how you can find these using your calculator. To find binomial coefficients using your calculator, the first thing you need to do is press your math button. And when you press your math button, this is the screen that will show up. It'll be math, and you'll see the frac, all this stuff. But the very last one says PRB. PRB stands for probability. And a lot of these things do come into play in terms of probability theory, so in calculations. So we have that. So you want to arrow over to PRB, which is probability. And then when you look down, you'll see the third one down is NCR. That is N choose R. So what you can do, if I wanted something like 9 choose 6, 9 choose 6, like we did before, I would put it into my calculator as 9. Then I would go to the NCR, so NCR, and then 6. And then you can press enter, and when you do that, you should get the 84. Try this with something like, let's go 10 choose 4. Go ahead, do that in your calculator right now. Make sure that you get the correct answer. In this case, when you did that, you should have come up with that equal to, you would put it as 10 NCR 4, and that comes out to be 210. So now we get to what's called the binomial theorem. Okay, we're going to let a and b be real numbers, and n must be a positive integer. Then I know a plus b to the n power is going to be, those binomial coefficients were formed by what we just saw. So it's going to be n choose 0, a to the n, plus n choose 1, a to the n minus 1, b to the first, plus n choose 2, a to the n minus 2, b to the second, that is a 2, plus, and this pattern continues all the way down to n choose n minus 2, a to the second, b to the n minus 2, plus n choose n minus 1, a to the first, b to the n minus 1, and finally plus n choose n times b to the nth power. Notice that in the first one and the last one we don't have the a and b. We don't have the b here because that would be b to the 0, which is 1. And the same thing would be true here. That would be a to the 0. which would be 1. Now, you can shrink this whole thing down by thinking of it in terms of sigma notation. We can write that as a plus b to the n power is the sum, as k goes from 0 to n, of n choose k, a to the n minus k, times b to the k. Now, this form of the term is really going to come into play as we do some of the problems moving forward. Now let's take a look at some examples. Before we go on to the stuff that I have down here, I want to recall this right up here. And this is actually what we just had on the last slide, but I want to have it written there. That is a plus b to the n is equal to the sum as k goes from 0 to n of n choose k, a to the n minus k, b to the k. And really, when you're going through and doing a binomial expansion, what's going to be key on this is identifying what's a, what's b, and what n is. Well, n is always easy. That's the power. A is always what's in the first part, and b is always what's in the second part. Please notice that I have this as an addition, because you're going to want to go through and modify. If it's a subtraction, you're going to want to change that so that it is written as an addition problem. And then I'll just put whatever is in the a spot here, whatever's in the b spot there, and whatever is the power will go here, here, and here. So I look at this first one. I have x plus 3 to the 4th power. Well, I know in this thing right here, I know a is equal to x and b is equal to 3. And so this is going to equal the sum as k goes from 0 to 4 of 4 choose k, x to the 4 minus k times 3 to the k. And so if I expand that out, with the summation by starting with k equals 0 going up to 4, I get 4 choose 0, x to the 4th, plus 4 choose 1, x to the 4 minus 1, which is 3, times 3 to the 1st, plus 4 choose 2, x to the 4 minus 2, which will be 2, times 3 to the 2nd, plus 4 choose 3, x to the 4 minus 3, which is 1, times 3 to the 3rd, plus 4 choose 4, times 3 to the 4th. At this point, I will now evaluate each one of these, and those will come out. If you do those on your calculator, you will get the numbers that are in red. So that will be 1 times x to the 4th, plus 4 times x cubed times 3, plus 6 times x squared times 3 to the 2nd, which is 9, plus 4 times x times 3 to the 3rd, which is 27, plus 1 times the 3 to the 4th, which is 81. And so when I simplify that, I will get x to the 4th plus 12x cubed plus 54x squared plus 108x plus 81. Let's take a look at a second example. In this case, what I have is 3x minus 2 to the 4th. Now remember what I said up here, that I want to think of that as an addition. So minus 2 is the same thing as 3x plus a negative 2 to the 4th. So in this case, a is 3x, b is a negative 2. And again, we're going to use n as 4 again on this one. And so this is going to be, this binomial expansion will just be the sum as k equals 0 to 4 of 4 choose k times 3x to the 4 minus k power times negative 2 to the k. So again, if I write it out, expand it as we did the previous one, I will have 4 choose 0 times 3x to the 4th plus 4 choose 1 times 3x cubed times negative 2 to the 1st plus 4 choose 2 times 3x to the 2nd times negative 2 to the 2nd plus 4 choose 3 times 3x to the 1st times negative 2 to the 3rd plus 4 choose 4 times negative 2 to the 4th. Again, since I use these same, both of these were to a power 4, I already know the binomial coefficients are 1, 4, 6, 4, 1. So it's going to be, when I start simplifying it, 3x to the 4th, this first one is going to be 1 times 81x to the 4th plus 4 times 3x cubed is 27x cubed times a negative 2 plus 4 choose 2 is 6 times 3x squared is 9x squared times negative 2 to the 2nd is a positive 4, plus 4 times 3x to the 1st times negative 2 to the 3rd is negative 8, plus 1 times negative 2 to the fourth is a positive 16. And so when I simplify that, that will be 81x to the fourth minus 4 times 27 times a negative 2 is going to be minus 216x cubed, plus 6 times 9 times 4 is going to be plus 216x squared, minus 96x plus 16. So there would be the expansion that we would have for 3x minus 2 to the fourth power. Again, just to reiterate, the things that you have to remember on this. You have to go through and identify what A is. You're going to have to identify what B is. And you always want to go through, like we did down here, where we made this from a minus 2 to plus a negative 2. You're going to want to make sure you do those. And then you have to identify what N is, and then just plug that in and write it out as we did here and here. Write that out and then do the expansion after that when you're asked to go and do a full binomial expansion. Now let's take a look at some other examples. In this case, what we have here is we want to find the fifth term of 2x minus 5y to the eighth. Now, what I want you to remember on this one, every term, what you saw in that summation, every term of a binomial can be thought of in this form right here. The n choose k, a to the n minus k, b to the k. That should be, again, familiar to you because you've seen that. It's the stuff that's right after the summation symbol. When you had the sum as k went from 0 to n. It's that portion. So in this case right here, they want us to find the fifth term of that. Well, on this problem, I know that n is 8, a is 2x, and b is going to be a negative 5. And so I know every term here is going to be 8 choose k times 2x to the 8 minus k times negative 5y to the k. And this is a setup that you're going to need to do for any problem. Anytime they ask you for a specific term number like this, you're going to want to do this because, and actually in both examples 3 and 4, the key is identifying what you put in for k. Now in this case, I want to find the fifth term. Well, if you remember from the binomial expansion, my first term had k equal to 0. That means my second term is going to be k is 1. My third term is k is 2. My fourth term is k is 3. And the fifth term is going to be k is 4. The term number you're trying to find, k is always going to be one less than that. So on this particular problem, if I want to find the fifth term, I know k is 4. So what I have to do is I have to find 8 choose 4 of times 2x to x to the 8 minus 4 times a negative 5y to the fourth. So what I'd like you to do right now, well, this is going to be 8 choose 4 times 2x to the fourth times negative 5y to the fourth. So what I would like you to do right now is pause the video and I want you to simplify that expression. Okay? Welcome back. You should have gotten 700,000 x to the fourth y to the fourth. The way that works is this. The 8 choose 4 is 70 times 2x to the fourth is going to be multiplied by 16 x to the fourth, and negative 5y to the fourth is going to be 625 y to the fourth. And so when you multiply all that out, 70 times 16 times 625 gets you 700,000 x to the fourth y to the fourth. So that would be the fifth term of that binomial expansion. The other thing they're going to ask you to do is they're not going to tell you what term number you want, but they're going to tell you they want you to find, they'll give you a binomial, some binomial raised to a power. In this case, we have r minus s squared. Notice that. And we want to find the constant, find c, the coefficient of r to the sixth, s to the eighth. Now the first thing you might notice saying, wait a second, I thought these powers were supposed to add up to 10. Well, we have an issue on this one because it's an s squared. Okay, that's going to make a difference. So if I look at my that general term, it's going to be 10 choose k, r to the 10 minus k, s squared to the k. And now what we have to do is identify what value of k is going to make this true. Well, in this case, we want the power on r to be 6. That's going to be when k is 4. And if I put 4 in for k, power to a power, we multiply it, so that will give me s to the 8th power. So, for this particular problem, we're going to let k is going to equal 4. So what I'm going to have is 10 choose 4 times r to the 6th times s squared to the 4th power. Now really all we're looking for is the coefficient. And in this case, since we don't have any number with the r, the s, no coefficient on those, really the only value we really need is the 10 choose 4 on this one. And so you can go to your calculator and just do that. And when you do that 10 choose 4, that does equal 210. So C, in this case, would be 210. Now let's look at Pascal's Triangle. Pascal's Triangle is a way that we can use to go, another way to do these so that we don't always have to go to the calculator. Now Pascal's Triangle has some patterns in terms of its development that are nice and work out, but it is not going to be necessarily the most efficient way of doing things. It'll be quick for the smaller powers that we have, but it will not be as good for the larger powers. And what I want you to know here, this is Pascal's Triangle, and I have each row in a different color for a reason, and we'll talk about that in a second. But the way it's formed is that there will be ones, the first term and the last term in each row is a 1. Okay, and the way we go through, if you're not familiar with Pascal's Triangle, the way we fill in a number, like this 2, it's the sum of the two numbers above it. So 1 plus 1 is 2. And then I just work my way down. So 1 plus 2 is 3, 2 plus 1 is 3, and then we have the 1. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. And we can continue working our way down. So I have given you the first 6 rows here. But you can add on 7, 8, 9, 10, whatever you want on there, okay? Now at this point, I would like you to go and turn back in your notes or look at those expansions I asked you I have available when we took a plus b to the 1st, 2nd, 3rd, 4th, and 5th power. And look at those expansions. And look at those expansions, specifically look at the binomial coefficients and compare them to the rows of Pascal's Triangle. What you should notice on here is that this 1 and 1, this row right here corresponds to a plus b to the 1st power. This row here corresponds to a plus b to the 2nd power. This row is a plus b to the 3rd power. This row is a plus b to the 4th power. Now remember, these are the coefficients that you have there. The next row does happen to be the coefficients for the binomial coefficients of a plus b to the 5th power. So looking at that, you probably can recognize that in the next one, the last row that I have there, this would also be the coefficients for a plus b to the 6th power. So what this does for me is it gives me a way to go through and write out that expansion without necessarily having to go through and use the binomial theorem. And we can just use Pascal's Triangle to assist us in that writing out the expansion. For example, let's say I wanted to go and write out x plus 2y to the 5th power. Okay, now remember on this, you have to remember your patterns, that the powers on A started at n and worked its way down to 0. The powers on B start at 0, worked their way up to n. So in this case, A is x, B is the 2y. So I'm going to have powers on x that start at 5, work its way down, and powers on 2y that are going to start at 0 and work their way up. And so I know this is going to be, because I'm looking at x plus 2y to the 5th, I'm going to be looking at this fifth row. This fifth row is going to form my binomial coefficients. And so I know that is going to be 1, the first one is going to be 1 times x to the 5th, plus my second one is 5 times x to the 4th times 2y, plus 10 times x cubed times 2y to the 2nd, plus 10 times x squared times 2y to the 3rd, plus 5x times 2y to the 4th, and then I have to add on plus a 2y to the 5th, 1 times 2y to the 5th, which will equal x to the 5th plus 10 x to the 4th times y, plus 40 x cubed y to the 2nd, plus 80 x squared y cubed, plus it's going to be 80 x y to the 4th, plus 32 y to the 5th. And that would be that expansion. So in this case, I didn't necessarily have to go through and calculate and 5 choose 0, 5 choose 1, 5 choose 2. I can use the row of Pascal's triangle. That is 5 choose 0. That is 5 choose 1. That is 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. So I can use the triangle to help me out. Now again, that triangle works. It will always work. You could expand it as long as you want, but recognize that this is going to get pretty big as you work your way through this. So, but you should be able to use Pascal's triangle to write out a binomial expansion as well. Now this does conclude the video for this for 10.5. So with that, I hope everybody is doing well, and I will see you in our next class.